Hello everyone. So our problem statement is to build a model to predict the electrical energy output of a combined cycle power plant. So we have been given with 9568 observations. The features we have given are atmospheric temperature, ambient pressure, relative humidity, exhaust vacuum, and the last one is the output parameter, that is the energy output. So here if you see, we have been provided with the input features as well as output target. So as we have both the values, so it will be a supervised machine learning. Along with that, we can see we have more than one feature. So we will use the multiple regression to train our model. Again, as we have sufficient number of observations, right? 9568. So we won't be going ahead with the k-fold validation set. So we will create one fixed validation set only for our model. So if I segregate the data, right? So 80% of the observations will be for training set, 10% will be for validation set, and 10% will be for test set. And we are considering three models here: model 1, model 2, and model 3. Model 1 will have four features, all the features. Model 2 will be having two features, that is atmospheric temperature and vacuum. And model 3 will be having three features: temperature, ambient pressure, and relative humidity. Now first we try to do a scatter plot for all the features. And if you see here, right? So energy output, it decreases with increase in temperature, decreases with increase in exhaust volume, vacuum, then increases with pressure and increases with humidity. Now this is the data segregation as I have already talked about. So training set is of 80%, validation set 10%, and test set is of 10% data. Now coming to model 1, so we took the training set, we did the regression uh, multiple regression analysis, and we came up with this table. So here all the coefficients along with the fixed intercept value has been provided, and along with it we can see r square has been given as 0.92, which is quite significant. And also the p value, if you see, those are less than 0.05, so we can conclude that all the features are significant for the energy output. Now taking these coefficients and intercept, we will calculate the energy output, a predicted energy output. So we just put the formula as 80 into the coefficient, then vacuum into coefficient. Similarly for other two features, along with it we just added this intercept, sorry, and then we came up with the P hat, that is energy output hat, and we calculated now the errors as well. So mean squared error, mean absolute error, and mean absolute percentage error. So those are coming out to be 22.9, 3.65, 0.08, and r square we took it from the other regression model. So we did the similar analysis for model 2 as well as model 3, if you see here, and then we just try to compare the three models. So if you see here, right, all the values have been provided here. So we can clearly see that model 1 is having the highest r square value and the lowest error values. So 22.9, 3.65, 0.08. So we can conclude that model 1 is the best fit for our observation data, and we should go ahead with that model 1 only, having all the features. And we did the same analysis with our test set as well. So for test set, we have 10% observation, and we calculated the PE hat, and we tried to find the error values here. So yes, so we can go ahead with model 1. Thank you so much.